So the things we're talking about today is about data. What's data all about, and why is it so important? Everyone has data and wants to do useful things with it, make predictions, control their robots, drive cars, decide how to sell people things, basically anything that people are doing these days, they're using data to make those decisions, like I was talking about last time, right? But if you're going to be the data scientist person who helps a company, or if you're doing research, you're trying to figure out ways to process it, you need to have a bit of a finer grain idea of like, we need more data. I mean, more data is always better. So anyone ever says, let's throw away some data, it's taking up too much space, like try to stop them. It's like, don't get rid of the data. Let's try to save it or compress it or something, because it could be useful. But there are different types of data that are more useful for some things than others. So a lot of actually this lecture really is going to be about some terminology that helps you distinguish between different parts of that. And you've probably heard some of these, and some of you might not have. So people often just say data modeling. And that's when you're trying to kind of create kind of structure or information or bias towards the data and say, this is what this means, and this is what we're trying to construct a view of it that's going to be useful for something, right? But an important part of your data are the sources, right? Is like where it's coming from. Can you trust the data sources? Is it continuous sensors? Are they records that were created by humans? Is it an old archive that's been digitized, or was it created from data originally? These are all relevant things you have to think about when you're thinking about the quality of your data. Because if the data was created by humans in some way, it could be error prone, but it also might have really useful information in it, right? Right, okay, and data mining. So this course used to be kind of where they would fit in data mining, and it's still not used as much as a term these days, but it's still an important thing to know about. That usually refers to trying to extract patterns from large databases. So usually there's a database there, right? And so when they're trying to decide what ad to show you on Facebook or in your email and your spam box, they want to mine different data they have and figure something out, find a pattern in there and use that to say, oh, he's going to buy this thing, so I'll send you this link, right? But it also could be trying to find patterns for crime or anything, right? But it usually means something static. So there's a database that exists and they're mining it for information. That's why they talked about it that way. You're trying to dig out something. Most machine learning and things they talk about these days doesn't really fall into that category. Although you can use machine learning to improve data mining, but it's kind of this task of looking at a large database that exists and extracting something. There's analysis kind of more general that you're analyzing it and trying to come with some analysis of your data, an explanation, or help you use it for a useful purpose. So big data used to be a big thing, and it's still kind of mentioned, but it's not like, oh, everything's big data. So big data has this terminology of what it becomes big, and maybe for you guys it's starting to become strange that we ever talked about megabytes of data or kilobytes of data. I had computers that worked on kilobytes of data when I was a kid. But now it's always like even gigabytes are nothing, right? I have terabyte drives everywhere. And if you have a lot of data, you probably have hundreds of terabytes or petabytes of data. It really becomes tricky then. Why did my screen change? So there's no hard line about what makes data big, and gets you to the point where you need to start thinking about how to parallelize it and run across networks. That line will change based on computer power, right, and methods that people have. But they have these concepts that they have in big data, which if you're going into industry in this kind of area, you should find out more about. They don't really relate much to the methods we'll need for this course, because we're going to assume our data isn't so big. We want to focus on the algorithms for analysis, right? But they talk about the data could be big because there's a lot of it, obviously. So social networks, medical data, financial data, satellites, anything that's automated where you're collecting sensor data all the time is very big. It's large volume. But it could also be big because of the velocity. So that's streaming data is arriving all the time. So sensors on your car, and there's hundreds of sensors and they're all continuous. How much of the data can you store? You can't keep all of it, right? So we talked about time series and real-time systems. There's separate courses on that. We will touch on some of the methods that you need to do if your data is streaming. But once it becomes huge and streaming, you get other choices you have to make about throwing away data as you're using it. It also could be the variety of data. The data is difficult because there's so many different modalities, we call them. So I should write that down there, right? We might talk about the mode or modality of the data. That we've got images, we've got video, we've got audio, text. These are very different types of information, and the algorithm that's good at processing images is not the same algorithm for text, right? So how do you combine this? And this is a very active area right now, and we'll touch on this more because each algorithm is really good at doing certain types of data, and you can kind of use it for one or the other, but to combine and build a system that can take input from just numerical data and videos and text at the same time, that's kind of tricky and interesting. So there's a lot of research there. Kind of secondary things that people talk about in that field is veracity, variability, complexity. So I guess I didn't have any extra comments on those ones. Obviously, whether you can trust the data. So we will talk about that if there's bias in your data or your collection that you have to worry about. So we'll get more specific about different types of data now. So we're going to break data into these 4 different types: nominal, ordinal, interval, and ratio data. You might think data is data, but it matters what kind of data it has. So nominal data is a bit more of a qualitative type, and it has some kind of measurement, but it's not something that you can say precisely or give an order to. Like something is blue, and you can get more specific. What kind of blue? What frequency? But blue, red, green don't really have an ordering. They're real labels you can apply to something, and yet you can't sort them. You can't give some kind of precision. Is blue bigger than red or less than, right? So it's all about these 4 different types of data. Might seem just like semantics, like just words for breaking things up, but they have real implications because you can't use different operators on them, right? So nominal data, the only things you can do is say, are they equal or are they not equal? And that is a bug. Right, we can say, are they the same color or are they different colors, right? And so these are things that they're labels. We might also call them categories, right? That we'd say, I really should get my pen out, that we'd say we're applying a category to this item, and they're not sortable, but they're meaningful, right? So often sometimes the label we're trying to predict or classify is some nominal thing, and we just need to be aware that sometimes you can't sort them or do some numerical operations on them. So ordinal data is data where you can rank between them, but you can't do anything else, right? So it's something like high, medium, low, right? So you can have a column in your data that's legitimately collected, and maybe it was created in a very precise way, but it's really just something like high, medium, low, high risk, low risk, right? We were in the COVID regions now, at least in Ontario. We had regions before the holidays where some regions were in red and blue and yellow, and they were labeled with colors, but there was an ordering, right? Because red was worse than orange and yellow, and gray was worse than red. So that's an ordinal ranking with kind of a nominal label. So we can say if they're, in this case, we can have equal and not equal. We can also have an ordering of less than or greater than. And these could be numbers, but you could say that you're given numbers and you can only sort them, but you can't say that high is twice as bad as medium, right? That's the distinction here, right? And just because you give it a number 5 and medium is a number 3, that doesn't mean high is 1.5 times worse than 3 than medium, right? So if it's an ordinal data set, you have to be careful if you just replace it with a number and then assume you can just double these and this means like twice as bad, right? That would be incorrect. So then with interval types, this is more of a quantitative measure, and it's kind of like that they have equal size units, temperatures is the best example for this, where there is a range, and you can say that some numbers are higher than others, and there's an ordering. But the way you interpret it depends on the units you're using, right? So we can say that one object is hotter than another, and so it has a higher temperature. And whether you use Celsius or Fahrenheit, you'd be able to tell, how much higher. But because of where these things are set, they're determined over some interval, right? So the entire range of this temperature has a limit, and so you can't say that twice the temperature means they're twice as hot, right? You can say that for positive temperatures, but when you talk about a cold, something below zero and something above zero, you have to be careful how you compare them. So the magnitude may not be that meaningful. So what we're talking about is that every change in the values is representative between the difference between some numerical value, not something absolute, right? Right, and so that's for Celsius and Fahrenheit scales. That's true, right? Because you can put any temperature in there, but they don't have an absolute zero range, right? Whereas you know what the coldest temperature is it minus 257 or something? But it affects the way the numbers are set up. Whereas if you use the Kelvin scale, which scientists and engineers do with very cool things would use, you'd set it to zero means zero. Like nothing can actually be lower than zero, and so you don't have that worry. And so now you come to the kind of number we kind of think of by default, that if you got some measurement, you can do anything on it. You can double it and say this is twice as much of the thing than the original value, and these are called ratio data. And it has a 0 point, so scale is kind of already built into it. And we use this for actual things that we're measuring in the world that we can measure, and that where zero makes sense. And so it means that you can do these multiplications and other comparisons, and they make sense, right? So for money and distance, really a lot of the data is like this, but you just have to be careful that it's not all of the data is like this. And you can get into calculation errors if you forget that. The difference between the interval and the ratio types is, just think of the difference between doing your temperatures in Celsius versus in Kelvin. Okay, so then the data, so that's the different types of data you could have. All the data can also be structured, so we're often going to deal with structured data in different types. So you might get data that's like set up like genetic data. You already know the different letters and elements it's in. It could be structured in a tree, so you know hierarchies of the objects. So they tell you, here's the data on vehicles and vehicles that are called cars. So your data might have hierarchies built into it. That's useful to try to leverage. And obviously your data could be given to you not as a table, but as a tree or some kind of description. So this is more to show like what you don't want or you want to convert. These days there's tools and libraries that make things very easy. So if this is just a tree described in JSON files, you can extract it and do machine learning on it, even though it's got this relational kind of connection. It also can be in databases. So especially when you're talking about big data and data mining, the data might be in multiple, tables. And so every table is kind of a different kind of concept, and there's fields in each one. So the employee table has different fields or features describing employees, and they're linked here. In this course, we're going to assume that everything, in essence, in the end, becomes a table. It's not really true, but you can always make it true by just adding more attributes and features. So we've got rows of data, so new data entries, like if you're talking about census data, you've got every person that filled out the census you have information on, their address, their income, how many children they have, etc. And that the features, the columns, the attributes describe these different things about your data items, right? We also call these the samples or the instances. And the columns, we'll call them attributes. I'll say features a lot because that's my background, how we talk about them. But dimensions is also a big one that we'll refer to these as dimensions, where essentially you can think about every one of these dimensions is an actual dimension of a physical space, and the samples are points in this space, right? So you've got 100 different pieces of information about individuals. Every person that does the census is a point in this space. That's 100-dimensional size that you can't see. But then we'll talk about distances between points in that space, right? And if that makes your head spin, that's okay. Just go back and think about it as a table with a lot of columns, like in Excel or just some table. But the distances we're computing are going to use these as if they're dimensions, right? You just can't visualize this as easily. Okay, so we have some data. We've talked about kind of where it came from and what it is. And so what if there's something wrong with it? So you talk about data cleaning. We're just doing kind of a brief overview of some of the high-level methods, and we'll get you to kind of play around with them in the first assignment. But you always need to do these things to assess your data, try to figure out. These are things that you have to kind of assess qualitatively and figure out by looking at the data, even plotting it and trying to get an overview, doesn't make sense at all, right? So if you've got plots and you know they're going up, it's like, okay, that seems fine. But maybe some other data has weird spikes. Like, can we explain these spikes? Like, is that just actually what happened, or was it a result of something weird that happens? Some states have stuff like that, right? Where you'd say, oh, there's like a whole arbitrarily strange structure in the, if I do this, does it zoom? Yes. In the data, you'd want to figure out why that is, right? Because it looks unnatural and you can kind of just eyeball it. It doesn't tell you how to fix it, but it tells you there's something wrong, right? So those are fine things to do at this first stage. Like, is there something wrong with it? Is it consistent? Can I understand it? Maybe the data isn't interpretable because it's 100-dimensional space data or something. So you may not be able to do all these things right away. Interpretability is hard. Usually you can't do it. But missing data is kind of a particular one that's interesting because you can do something about it. Maybe you don't always want to, but you could. Right. So say that your data is missing values, right? So if we had one of these and there's just totally a gap in the data that's missing for some part. Obviously, you could try to fill it in, right? You could say that that something's missing. You want to make a guess as to how to fill it, right? You have to do something because there's an incomplete part of the data. You've actually got something missing, and so if you try to if you learn about that part where it's just zero, your model will just say, okay, it's zero there. I guess the problem's gone. COVID just vanished for a week somewhere because they had no data. Right? That's not true. So you need to do something. Either tell your model to ignore that part of time somehow, or fill it in with a guess. That has its own problems, but it is something you can do. So there's various ways to do that. You could talk about, taking the average value, right? Take the mean of the values that are missing and fill it in. It's about different ways of just summarizing data. So we start with means and variance, and then talk about some other kind of simple methods that you can use. But which one do you use, right? Do you take the highest value, the average value, the one that's the highest over general? It really depends what you're doing. And no matter what you do, you've got to tell everyone. So when you make a report that says, okay, we filled in the missing data with the average, running time average from other regions, you've got to make it clear, because otherwise you're basically altering the data and faking it. But it doesn't mean you can't do it in general. You just have to be upfront about what has happened, right? A more complex thing you could do would be to actually make predictions or interpolate the values, right? So if you're missing values, we've got, something like this, and it went down to zero, rather than filling in with the average of what we had before, which might give you, something weird like that, you could fill it in with what you'd predict to happen based on the existing trend and the noise and all that, right? So that'd probably be more reasonable, even though it's still fake data that you're adding, right? So people really do this, even though it seems like it's going to cause a lot of problems. So I looked up some kind of sources for this, and like the EPA has this very dry 150-page document, which I put on Zotero if you want to look. But it has a whole section talking about these policies they have for doing that. So I just cut this out so you can see that this is the Environmental Protection Agency in the United States, right? So they do, checking, at least usually, maybe not the last couple of years, but they usually check for environmental, environmental problems and pollution, and they're regulating all these things. And so sometimes there's data missing, either because maybe a company's not collecting it, or something happened, or literally, the sensor went down, or a bear ate the sensor. That happens. What do you do? So they talk about interpolation. Just fill it in with some kind of model that you fit. You could use regression. You could use a really complex neural network. But make sure you account for like obvious cycles, right? Like day-night cycles or something like that, or the temperature average around there. Persistence is what they're saying. Just like pick what's the average that time of day and copy it over. So Google will tell you how likely it is the restaurant you want to go to is busy right now. They're using previous day's data for that to fill in and give you a prediction. Profiling is probably the more interesting one, where you say, let's build a model of what's going on there, including the weather and the situation, and other regions that are similar right now, and see if we can make a prediction by extrapolating from them and come up with it, right? So these are all things people do. They even put in their report, though, that you should not use this to cover the fact that you don't have enough data. So they say don't substitute data. If you're missing 10% of your data, don't use it to like replace the last 10% and make it look like you have all your data. You do this when you're missing a small amount, hopefully less than 10%, maybe 1% or less, and you've got to fill in a gap, because otherwise you can't fit your model. But you're going to have caveats about how you did it, right? About outliers, right? So a thing that's definitely going to happen is you're going to have outliers at some point to say this data point is just weird, it's outside the norm, and you have to deal with it, but it's not in a meaningful way, right? So we will talk later in the course about anomaly detection, which is detecting outliers because they're important, like people who have different, behaviors, and maybe they're having trouble, or maybe they're criminals, or stock trades that are irregular and they might be illegal or coordinated. But in some cases, it's just like, well, okay, India had a very big spike here. They probably didn't have 2,000 cases that day and only 300 the days around it. It was probably, they changed the way they were counting. Maybe at that point they took, actually, since it didn't continue, I don't know what that means. You'd have to find out, right? Or just remove it, right? This one you'd probably say, okay, it's definitely not normal, so let's just remove it. But how do you detect these ones, right? Should we remove this one? Should we remove this one? What about this one, right? At some point it is subjective, and so you have to basically justify whatever you're doing with statistics or some kind of model or a statement, right? But yeah, it is biased, as someone was asking, because you're putting in your own assumptions, your own knowledge about the system into the data as you adjust it. But if you don't do these adjustments, then your model can't just process everything, and it will make the wrong assumption, right? If we just use it with this point, our model will kind of veer up here for no reason, and it will give us the wrong conclusions, right? So you can't avoid it, but yes, it introduces bias. So removing samples is the easiest part. You could smooth over them. So these other ones that are kind of more erratic, you probably want to, do smoothing. So we have some slides on smoothing, where you'd say we could take a histogram of the data. So there's a histogram. You can just call a histogram in your favorite language once you're given your data, and you create it into boxes that have a range, right? So all the data points in here, even though the data is actually like this, we're just going to box them into a histogram and say, okay, at least data points near each other should be kind of similar, hopefully. And then if you take the average of points here, you can use that. So histograms are useful for a bunch of things. We can use them to help us smooth it. We can use them to help us detect outliers, right? So something that might not look like an outlier in the original plot, it might be more clear in the histogram, because then you get an entire range that's blocked off, right? This isn't necessarily the best example, but viewing your data as a histogram just personally beforehand and doing some processing is a good way to kind of figure out what's missing. I mean, the first thing you do is you look for zeros, look for like missing data entirely, but these are simple ways to visualize some of your data and try to figure out what's going on. So you could smooth them by replacing them by some other value. So for an example, we've got some data here with numbers that we've got sorted, but the frequency is kind of not that regular, right? So if we bin them into 3 bins so that they're kind of just equally sized, and then replace them with their means, that would be one way to do it. But that would be kind of overkill, right? So you're taking the average of each bin and just saying, well, here's the data. It's just like this, right? Well, it's not even that. It'd be just straight lines for there. So that's an approximation of your original data set, but it's a consistent thing to do, right? You would usually want to do something a bit more precise in different regions, but that could be one of the ideas. A better way to do it, right, would be to say, let's not just take, a predetermined division of the data. Let's do like a rolling average, right? You can create a window and move it over time, and then replace your data with something that is averaged over a series of values, right? So instead of taking the first 2 and replacing them with some value, you could take, I forget what we're averaging here. Probably pairs of values. 3, 2.6, right? So I forget which one we're averaging. So the second value is an average of the first 3, right? Somewhere between 1 and 3, right? So you take a number of points, take their average, and that becomes your near point, right? Take a number of points, take their average, and it becomes your near point, right? So this is a window-based smoothing where you're taking at least nearby neighborhoods and you're just smoothing it. And so the size of that window and whether you're using the mean or the max or something else, these are all choices you can make as you're adjusting it, which you have to justify, but they're all ways of making the data smoother. Quite simple things. Simple, but you have to figure out what the right way to do is that another issue that will arise is that the scale is different, right? So if you're doing this numerical data of people and you want to compare if people are similar, right? You obviously can't compare. You've got numbers like age, which is 0 to like 110 or so, 115. You've got income, which could be in the thousands or millions. You've got, addresses. You've got numbers of children, which would just be a small number. So all these numbers obviously aren't comparable directly, so you have to normalize them, right? So this idea of normalization is actually really important. And the way you normalize it can bias your data as well. So we're going to start with our values, x's, right? That's our rows in our table are x, and the columns will be y most of the time. In this case here, we just imagine we have a single ratio-based measurement, but we have a bunch of numbers. And basically to normalize them is to say that they're all going to be in the same scale, right? So whatever your numbers are, say we're using income for people in the census, then we want to say, well, let's have all the income so we can compare them to other numbers, to age, right? And we want to make it so that all numbers are between 0 and 1, right? So we normalize age to 0 and 1, and we normalize income to 0 and 1. Obviously, one way to do that is just to take the maximum number that shows up here and divide all of them by that number, and then they'll all be between 0 and 1, right? That's okay. Min-max normalization is slightly better than that, because at least you take what's the highest number in our data set and the lowest number in our data set and divide them from that, right? So if we've got data on age, right, and everyone in our data set is above 5 years old and no one's above 100, no one's below 115, we'd have 100 years, but we'd subtract 5 from them, so the kids are all at least 5. Everyone, the youngest person is 0 and the highest person is 1. right? That's kind of what you would come up with by default if someone told you to normalize it and explain that. So this works. Comparison still works. Something that's higher than two values that are in a certain order will stay in the same order. A real problem happens is that what if you ever get a data point that's outside this, right? So what if we get a value x n plus 1 that's more than 150 in a really old person? Suddenly their value will be 1.1, right? So this is a problem if you don't know what the min and max of your data are, and there could be data outside it. But it works for what it works in. You could subtract the mean. So another just a modification was kind of even simpler version is just to subtract the average. So at least all the data points are shifted around 0, right? So you'd say that any data points that are on the line here, these would be the kind of most average in terms of it. And then the lowest data point would be somewhere negative and the positive would be positive, right? So this is a normalization as well, although it doesn't give you a fixed scale. It gives you a fixed comparison level and saying, if they're positive, they're above average. If they're negative, they're below average. So that's kind of normalization. The one you probably should normally use is called Z-score normalization. So that says, take this mean shift idea, which says, okay, we're shifting to the mean, so the numbers are 0, positive or negative, given if they're above average or not. But then divide it by the deviation, the standard deviation, right? So this means that most data points will really be in that scale between 0 and 1. And if they're kind of if their distance between each other is more than 1, then they're more than a standard deviation apart, right? So then there'd be kind of this very unlikely, there'd be very different points. So that's a way that often helps because it tells you whether a point is normal or like in the same kind of neighborhood of them. So essentially, if the data is Gaussian or a normal distribution, then this would come out to be a normal Gaussian. And if it's kind of skewed, you'll be able to tell that very quickly. So people call this standardization or the standard score, but it's officially called Z-score normalization. So this is useful to get around that problem of where there might be a new value that's higher than you've ever seen. So if you're doing for age and you want to talk about people and their age and average age, it'd be good because even if you get someone who's older than you've ever seen before or younger than you've ever seen before, it wouldn't throw off your number. The numbers would still make sense. And if it matters that similar points are near each other, it's going to give you the right scale. But it's not always the best choice because it could be that that some points get closer together, right? So what you're doing here is, in any normalization, you're kind of doing this, you're squishing data points together that used to be far apart, right? And so depending on the precision of your computer and how you're using it, if suddenly now all the people are within 0.01 of each other and before they were apart by 10, that still matters in terms of your comparisons. If 0.01 is considered small in your model, they'll seem like they're identical, even though they're not, right? So anytime you're normalizing, you have to make sure you think about what you're squeezing. You're losing precision between certain values that are now closer together. If you're doing large, like money or safety critical things, it could be really important that the differences between certain data points are seen as far apart. So if you're doing this type of normalization for Z-score on forces, I forget where this comes from, that it has this effect of creating all the forces to be kind of in a standardized way. And so so the shifting to the mean or Z-score have this kind of same effect that certain elements are kind of maintained if you're talking about forces and movement, and it kind of normalizes them to this magnitude 1 scale. So we have an example there that you can look at numerically just to compare. It's very small, so we can find some better ones on the web, like better numbers or plot some ourselves. Just to show that if you have your original data set and you use the different values, what is it going to look like, right? So the original data were for the min-max, you are always making between 0 and 1, and it has its own mean and standard deviation, but it's this kind of scale. And the other ones kind of maintain the 0, but they change the scale of what the positive and negatives are. So comparable, like telling whether how to sort them or whether something is twice as big as another wouldn't change, but these changes would tell you something different. And I guess when you do Z-score, you'll actually also get it so that the scale, twice the difference here, will not tell you that it's twice as big, but it's kind of twice as far away from the average, right? So distances mean different things depending how you've normalized it. For COVID, there's interesting factors, right? Because there's population, there's infection rate, there's R numbers. Not all these numbers are comparable. So you have to think about which ones you want to compare and how to do that. So that's why I like this this plot. It's on the CTV website, but it lets you do things now. We can do it by the raw number or per million, right? So essentially they've normalized it. The one we were looking at was per million so that everybody was comparable. But if you look at the actual numbers, you get completely different numbers, right? California is the worst and Texas is next and New York is next, but that's because they're large, right? If you look at how well everyone's doing in terms of per capita, how many people you could expect, the states are a different order, although California is still second, so that tells you that California is not doing well either way. In Ontario, sorry for our international people, this one shows, this plot showing every state and province in North America because they kind of have similar ways of approaching things. So it is useful. In Ontario is not as bad in terms of per capita, but in terms of number, obviously Ontario is the highest because they have the largest population. So normalization is important for all these things. An interesting thing to think about for COVID, and we're going to try and use that for some of our data sets, so it's good for you guys to start thinking about it, is what other things could you normalize for? What other problems might arise for COVID data, either from missing data or normalization or anything like this? Does anybody have thoughts or concerns or? Climate, age. So if you're saying age, you could have the average age of the population, right? Could be very relevant because if there's more old people in a country, there's more people who are going to die, even though maybe in a younger country, more people will get it. So the way you use age in your data could actually influence a lot. Climate, as people are talking about, it seems like northern countries are doing worse in terms of spread than equatorial countries. I was reading something the other day that like maybe vitamin D is related to how well you can fight off the virus. In countries with a lot more sun, people have more vitamin D. That they don't even know if that's true, but it's like there might be a correlation that's not even in your data, like how much sun there is or what's the latitude, right? So how to choose the right normalization method is an art, so you can read lots of different things about it, and there's advice on different types of data. We just have to kind of do that. Z-score normalization is kind of a good standard one to default to because it's used a lot of times, unless you know that your data has a very wide spread, and yet the precision between them is very important. So one thing you could do is just do a whole different bunch of normalizations and see what they make your data look like, right? So this is a plot from the Google crash course on data. I mean, there's so many instances of the content we're talking about this course online. So when I find ones, I'm just going to link them to you. And it's good to look up even additional sources. They go through some of these things and plot particular data sets. So you could say, here's the price of something, oil or wheat. And when you do different normalization, the plot changes, right? It still has this general structure, but the way you scale it will bring out different features, right? So if you just log everything, just takes a log and use that, you're going to see certain patterns that don't seem as significant, but they kind of jump out more. Whereas Z-score, let me see what it's doing. I mean, it shifts the numbers, right? So Z-score moves this all so that's zero focus. Can people see my mouse? Not that well. If I go to presentation mode, now you can see it better probably. The Z-score essentially centers it over zero and creates this scaling for the mean and deviation. So it looks similar, but the scale between some of the outlier points might be a little different than on this side. Right, you can also just clip it, so you can do dumb things like just throw some data away because it's too high, and maybe that's not dumb. Maybe it's useful because you know these are all outliers, right? But it's simple. And then this scaling to range is like min-max normalization that they've just basically said, here's the scale. Many things in this course are going to be represented as matrices, not as numbers. So we're going to have an entire matrix of data, and we're going to do the same things, right? And so we've got our data in this matrix A, right, rows and columns of features, and we want to normalize the whole thing. And so the way we could do that is kind of just doing the transpose, right? So A transpose of A, you're basically multiplying and adding all the values together and dividing them by n. This is a kind of very simple normalization just for a certain n that you've given it. If you do subtraction normalization, where you take the mean value out and then normalize the whole matrix, you essentially get the covariance matrix. So that tells you how each data point relates to every other data point in terms of, is this one, if they both go up or down, are they going to go in unison or against each other? So you get a covariance, which is when it's 0, it means they are basically identical. They will go up and down in synchronous, and any other numbers would tell you how they correlate. And under all these other normalizations, you get a different type of matrix. The correlation matrix is in there if you do z-score as well, but each of the data points becomes a correlation coefficient. So we can point you to more stuff on that, and you can kind of try it out on your data that's matrix formatted.